So I think we left off from what are the assumptions about that error term, right? So let's look at that and then at least get to the hypothesis test concerning those. In this case, we're only working with one independent variable, so it's concerning that beta one, no, the coefficient of x, no. So the important assumptions regarding that error term, no, and there's 4 of them. So the test significance in regression analysis are based on the following assumptions about that error term. And there's that model again, no? Y equals beta null plus beta 1x, and then the error term. The error term, so the assumptions about that error term is that the error term is a random variable with an expected value of 0, no? And the implication being that because B1 or B null and B1 are constant, then the expected value of B null would be equal to B null, and then the expected value of B1 would be equal to B1 since they're constant. Thus, for a given value of x, we obtain a simple linear regression and that's your formula, no? And then the other assumption, so that's assumption 1. The assumption 2 is the variance of E, the error term denoted by sigma square, is the same for all values of x, no? So what we're saying is that your independent variable predicts the value of your y variable, and that prediction is a random, you see, is the difference between that predicted value and the estimated value is going to be random, no? So the variance of y about the regression line is going to be equal to, and so we're saying that that variance is going to be equal for all values of x. There's let me in the meantime find that there's a chart that does it. Is it here? Yeah, this one here, no? What we're saying is this here, no? Here's your estimated regression line, and what we're saying is that each of the x values are predicting y, but that actual value of y, that is the variance of where that y value is going to be located, is going to be the variance for each of those x values are going to be equal, as represented by these confidence interval over each of the x values, no? And then the third assumption is that the values of E are independent. The implication being that the values of E for any 2 values x are not related. It follows that the values of y for any 2 values are also not related. To try to make sure that this is the case, remember in the beginning of the class we said that what? When you select the cases, your observations, you always want the selection to be random, no? So if you ensure that the selection of sample is going to be random, then the values that are going to be associated with your x and your y themselves are going to be random, and you see that's that's the importance of that assumption, that they're independent, not okay, let me go to the fourth one. Is the error term is normally distributed random variable for all values of x, which is really the statement that I was trying to grapple to describe in assumption 3, no? So they're related. Okay, so this graph illustrates those the assumptions that we just covered, no? So what we're saying is that all of this the sigma squared, no? All of these sigma squared are equal, right? And so that your independent variable at 20 would predict a values of y, and the variance of the values of y are going to be equal for each of the values of x that you have in your sample. No? And that the expected value is 0 here, yes, that's the first assumption. Okay, so note that the value of the expected value changes according to the specific value of y. That's what I was trying to say. And however, the probability distribution of the expected value and the probability distribution of y are normally distributed, each with the same variance. That's these guys here. And the value of the error at the particular value of x depends on whether the actual value of y is greater than or less than. That's the variance is the one that controls whether it's going to be above or below the expected value, which is randomly determined. Keep in mind that when we choose a linear model, we are just making an assumption. We're just making an assumption about the relationship between x and y, right? However, nonlinear models may very well provide a better fit, and so this is a caution, right? In this chapter, we're just focusing on linear relationship, but we have to be cognizant of the fact that there's other forms of relations, or nonlinear forms, which may in fact be the real relationship between the variables that we're assuming to be linearly related, no? Okay, so let's look at the test. So for a simple linear equation, this one here, which we've looked at before, tells us that if b1, right, that coefficient of x, is equal to 0, then that would mean what? That would mean that there is actually no relationship between x and y, no? So if you plug that 0 into that equation, you see that the expected value of y will become equal to your b null, no? So if your beta 1 is equal to 0, then that means what? There not the doesn't depend on the y is not dependent on your x, right? That there is no linear relationships between the two. And this would be your h, no? H null. If your beta 1 is not equal to 0, that is, and you go through your testing and you prove that to be the case, then we conclude that the two variables are related, and then you check the sign of the coefficient. If it's negative, the two are related, and inversely, if it's positive, then, right? Thus, we test for the significance of the regression. We must conduct hypothesis test to determine whether that beta 1 is equal to 0, no? The two tests we will use are the t and the f. But now we already know what the t test and the f test are, right? It's just that we're going to use them in the context of a regression, a linear regression problem. So both t and f require an estimate of the variance of that error term in the regression model, no? So again, and this is where the discussions we had earlier, right? If we get comfortable with using mathematical notations, then it makes it easier for us to discuss statistical equations. So from the assumption on the error term, we conclude that the variance also represents the residual. So this is an important definition, no? So that your variance is also your residual. So the term residual and variance are, right? That is the deviation of the y values about your regression line, yes? Because and now here's that notation again, right? Your sum of squares due to error is now going to be called sum of squares residuals because of that, no? And is measured, is a measure of the variability of the y values about the estimated regression line. So we're saying this one here, right? Here's your estimated line, and we're describing the relationships there, no? Okay. So it follows that your mean square error is sum of squares error divided by its degrees of freedom. We defined this before in the previous chapter. And then so that your sample variance is your estimate of your population, or your your population variance, no? And there's the formula that we use. So your mean square error is computed from your sum square error divided by the degrees of freedom, in this case n-2, no? Then you take the square root of that and you get your standard error of the estimate, no? Okay, so we'll walk through this using that example that we started with, and then we'll switch over and do a couple of exercises before the end of the class, hopefully. So for Armand's, we compute your sum squared error. We did in the previous slide, so if you need to, you can go back and look at that, which is 1,530, and your n is 10 given, no? So we have your mean square error. We can compute that by substituting, right? If you're substituting your SSE, which is 1,530, into your degrees of freedom, which is 8, 10 minus 2, then you get your mean square error, and then take the square root of that, you get your standard error here, no? Okay, so to use the t to test for whether that beta 1 is estimated beta 1 is significant or not. So let's walk over that. So the purpose of the t-test is to see whether we can conclude that what your beta 1 is not 0. So you want your beta to be non-zero, so you set your null to be equal to 0. Hence, when you reject your null, then the alternative hypothesis is what you're looking for. The hypotheses are going to be set as such. And then your beta 1, the least squares estimator of population beta 1, or your parameter, population parameter, follows the sample distribution with these properties. So expected value of beta 1 is your population parameter for beta 1. And then your standard deviation, right? That's your formula for that. And then the distribution form is normal, no? Again, this assumption of normality, which we started using in the chapter 6, is an important assumption when you're working with inferential statistics. The test statistic follows a t, right? Because of this, follows a t with n-2 degrees of freedom. So here's your formula to compute your t statistic, beta 1, which based on your sample, no? Divided by the standard error for a beta 1, no? And so where beta 1 is the estimated standard deviation of your beta 1. And again, I'm circling this equations, but as I said before, it's really when you're computing for these values, right, your standard error, your t-scores, it's really, once you know what those are, best you just leave the software to compute and you make the interpretation, no? So for the t-test, for the significance relationship between the student population and the sales, we use alpha at 0.01, okay? So recollect that the Armand's parlor case, we found that this is your equation, no? Estimated equation, which is your estimated value of y is going to be equal to 60, which is your intercept, plus 5 x, no? And your standard error, which we computed before in the previous slide, is 13.8. And so your variance is going to be 568. No, your variance is going to be 568. Hence, the estimated standard error of beta 1 is, if you substitute, right, you substitute the values into the equation, you get your standard error to be 0.5803, no? And then so your test statistic is going to be 8.62. Now again, I'm keep repeating that because eventually you will find this to be the case, right? At the beginning, you want to go through some of those manual computations, but that's just to gain an understanding so that you can interpret them in the printout. And then better we focus on solving or computing for those values using the software. Like in this case, we're using Excel, no? So the rejection rules these are the same ones that we've used before, only now we're using it in the context of linear regression, right? So um, uh, in the interest of time, I'm just going to skip over that, right? And so that we can go to the problem and solve it, and then I'll point them out in the printout, no? So you need to compute your t as we did this, right? We need to compute your t because that t is going to allow you to find the probability associated with t to determine whether you should reject or not reject a null, right? And if you're using the critical value approach, then you will have to figure out what's the t at the critical value and then determine again whether you should reject or not reject. So that's why I'm sort of bypassing this whole using the table routine, no? And then the same thing for you estimating your beta 1 interval. We know that we're estimating, so that beta 1 is just a point estimate. And to be confident and to able to see, have more knowledge about the nature of that coefficient, the x coefficient, then you want to come up with your interval estimate. And again, if you see this, we're using different notations here, but it's the same interval estimate formula that we've seen before. Only now I'm interested in beta 1, and then plus and minus, and this is your ME, no? Your margin of error term, right? And hopefully now when we see them, we recognize that, okay, that's the t-value at alpha half, and that's your standard deviation or standard error for your beta 1 in this case, no? And so if we, again, I'm bypassing the detailed description, and then deriving your confidence interval, right, by substitution. Once you come up with this, you can use the function to get, and this one you've computed from your sample previously. Substitute, and you get your no, your confidence interval, no? This is your, I'm sorry, this is your margin of error, and then plus and minus, you get your confidence interval. Okay, so that's your t-test, no? If we look at the f-test, it turns out because we only have one independent variable, then the f-test and the t-test play the same role of trying to determine whether that beta 1, that x coefficient, is statistically significant or not, right? When we will go to chapter 15 and see, we will see that, okay, the t-test will not suffice. So you will have to use when you have more than one independent variable, to test the validity of the model, you will use the F, and then you will use the T to independently check each of the betas if they're significant or not. No, I'm pointing to what's coming up ahead. But with the F test, we've already seen it before. We know the distribution of the F test, no? So again, you're with the only one independent variable, your F test is set up just like your T. It will provide the same conclusion. And here's our hypothesis, no? Beta 1 is equal to 0. If you reject the null, then the alternative, which is it's not equal to 0, then you check for the sign. If it's a negative, the relationship is the inverse one. It's positive, then the relationship is a positive one, no? However, with more than one independent variable, only f-test can be used to test for the overall significance. This is a repeat of what I said just a little bit ago, no? So the test statistic F with 1 degrees of freedom in the numerator and then 2 at the denominator, well, right, this is what the mean squared due to regression and mean squared due to error. The ratio of the two will give you your F statistic. where your mean square error is SSR divided by the number of independent variables, that's the degrees of freedom, and then your because in a linear regression we only have one independent variable is an important point. It follows that your MSR is equal to, right, because it's only one degrees of freedom dividing any number into one gives you the same number, no? Okay, so again, I will skip this part in the interest of time, and then we'll focus on interpretation of that one. And again, this is the structure of that ANOVA table that we saw in the previous chapter. We saw, so it shows up again. And the significance of this is what? Your SST is what? Your sum of squares totals, sum of squares total, right? It's total deviation. And then you're going to partition it, right? In this case, you only have one independent variable. So you're going to partition that sum of squares to the regression and then to the error. So that sum of squares R is what is the variation or variance due to the X, and then the SSE is the variation that is attributable to be the error term. Turns out that when we're solving from that equation that we looked at before, right? You're only solving for beta 1, right? And your estimated value of Y, and then the error term drops out as your residual, yes? And then your F, again, is computed as we've done before. You take your SSR and divide it by 1, and since your degrees of freedom is only 1, then it turns out that SSR equals to SS1, as we said in the previous slides. And then the mean square due to error, SSE divided by the degrees of freedom. And then now once you get that, you're going to divide the MSR into MSE to give you your F statistic. And then from there, figure out what the p-value is. Now we know that to get the p-value, you can use the table, but it's quicker and much more accurate if we use the F function in Excel, no, to come up with that probability associated with the F statistic, no? So if we translate or bring or substitute the corresponding values from our Armand's pizza, we see that the regression, these were computed before, no? So your regression, your SSR is going to be 14.2, your SSE is going to be 1530, total is 17,530, and then your corresponding degrees of freedom, yes? And then do the division and come up with your mean squares, and then you divide the two to get your F statistic, no? I'm repeating these because we would like to use them when we go and look at some of the problems, no? Okay. So, but some cautions is in order when we using the linear regression. So rejecting the null, which is beta 1 is equal to 0. Rejecting the null means, okay, that it's not equal to 0, that you're now establishing a relationship between the two variables. And concluding that relationships between X and Y is significant doesn't really enable us to say that there's a cause and effect, no? So always be careful with this one, no? Relationship is present between X and Y, but it's not a causal one. To be a causal one, you have to have some justification for it. Some kind of theoretical justification for it, or, you know? So for Armand's pizza, we cannot necessarily conclude that the student population causes, right? We say that there's strong relationships between the two in a positive one. So we can predict the value of sales by knowing the population, student population, but we cannot say that it is the population that is causing the sales, no? Also, another caution is just because we are able to reject the null and demonstrate significance, statistical significance, it doesn't conclude that the linear relationship is the true one. Yeah. It could be that you did not you rejected the null, but it doesn't really mean the true relationship may in fact be a nonlinear one, right? So we just want to be cautious about these, no? And then given the significance relationship, we can use with confidence the estimated regression equation only for predictions within the range of x values observed in the sample. And then for Armand-Spaller, we would use the regression equation only to predict sales for restaurants where the associate student population. So these are the lower and the upper limit of the population that were included in the regression. So we're saying that you restrict our estimate and our prediction to within the known values of x. No, if you go outside of those bounds, then maybe the linear relationship would collapse and would not be the appropriate one. So you wouldn't want to go too far out. Okay, so now I'll leave this in the interest of time. I'll leave you read this last part, right? Now, what I'd like to do is let's go and look at some of those problems in the homework, no? And just try to demonstrate, and I'll try to demonstrate that you can kind of shortcut these when you're studying now. You can kind of shortcut these parts where you're going to look through the table. You probably don't want to look at the table because when you're using a spreadsheet to compute your ANOVA, the probability and your F statistics show up. You don't need to go look at the tables for them, right? So it's knowing how to use your results is probably the better way to do it. So let's go to the problem. Let's see. In the interest of time, let's go do maybe a couple of problems there. Let me see. If I went to it's the same one that we use. So let's see. So if we went to problem, we did a couple of problems before, right? I think we did 2 and 3, yes? Yeah, I think this is the one we did. I posted about, by the way. Yes, last night. Okay, so we did 14.1. And we did 14.2.1 and 14.3.1. So let's go look at the other, what, 14.2, 14.3. So let's do 14.5, no? See what's there. Some of the problems are just testing our understanding of reading the ANOVA. So that, let's see. Okay. All right. So maybe this is a good one to do, no? So practice the interpretation. So here the problem says what? You may need to do technology. Okay, so we'll do that. It says consider the data. You're given X and Y values. And then it says compute the mean square error using the equation. So, okay, so it gives you the equations, right? But, and it's a good way to learn by looking at the equations, no? But actually, better we just use the Excel routine to compute and then figure out where those statistics are in the printout, no? We also use the Excel stat to do it. So to do that, we copy this is where I wished I try to figure out how to use two monitors so I can flipping around too much when I'm using single monitor. So I'm try to do that later next semester. Okay, so let's see. I already have the worksheet, so I'll just continue to use this one. No? So I'll open this. Then we'll paste the values in there. You first have to restructure your data file. So make that transpose, delete these two. We'll just leave it at that. Okay, so now we have the data in the right format that can be processed with the spreadsheet. And then there's two ways we can do it, right? If we went to the data, we went to the data tab, and then you go to your data analysis toolpack, and then you will see there, right? You will see ANOVA there. So we will use the but in this case, I'm looking for a regression. I'm sorry. So go find the regression and then get the regression and then open that, and then you're going to tell it where is your y values and where is your x value. So y values, right? And it's important that you put in the correct vector for the independent and the dependent variable, and then tell it you're using labels, and then let's see if I went to what's the confidence interval. Remember, it says are we going to, okay, it's 0.05, no? It's 0.05. And so let's see if I go back to Excel, right? CC is 95, so that's correct. And then I'll put the output. We can put the output, say, on E2 maybe, right? Then if you look on the bottom, you see all of these other. You want the residuals. Now, we haven't really in our coverage, we haven't covered the residuals, so we're going to compute them, and then you're going to read backwards, and then you try to get the interpretation, right? So in interest of time, we can see. So you can say, okay, compute the residuals, and you can also standardize residuals, and then give me the plot, right? And then click OK, no? Click OK, so that here's the residual plots, right? And then, so I'm just pointing out where you can have those plots. And then if you haven't read the chapter, go back and read the chapter to see what, how to you're basically checking for normality. So if those residuals are not kind of banded in a positive or negative relationship, but sort of, random, then that means your error term is normally distributed, and then you're fine, no? Okay, so once we get this, then it's a matter of interpreting the results, no? Which is important and quicker. And in the end, when you're working, that's what you're going to be doing. You're going to be quickly producing your statistics and then making interpretations. So here we're saying what? So what is your, hold that up, move this over. We're saying where is your computed mean square error. So now remember, we said that mean square, the error is also the residual, right? So that's where it can be confusing. Your software may use a different term. So in this case, it's residual term that we're looking for. So you can see that the residual in your mean square, MS, your mean square for the residual or the error term, this is your error term. is 3.03, no? So it checks, right? You could have manually computed using this formula, but once you know what that formula is, then actually it's quicker to just run the regression, and then where do you find those those statistics that you're looking for? So we got that, and then it says compute the standard error of uh, the um, the equation. So your standard error is over here. So let's see. That's your standard error. Then your um, mean square error. Yeah, mean square error, standard error, and then what else? Compute the estimated standard deviation, which is what, 0.05. Um, and then let's see. Um, that's the square root of your right. Okay. Then let's see. Um, it's this one, no? I think what can be confusing is this one. So if you right, here's your standard errors, no? So your standard errors for your, and here's your coefficients, no? So you got your standard error, uh, and then what? So use the t-test to test the following hypothesis. Beta 1 is equal to 0, or alternative, your alternative is that it's not equal to 0. You're going to use the t-test. So to use the t-test, here's your t-value, no? Your t-value for your x, no? Is your independent variable. So that's that one, right? And then what's your p-value? So your p-value is this one, no? Right? P-value, your standard error, your beta coefficient, and then what else? Is it matching? Yeah, it's matching. And then state your conclusion. So in this case, our alpha is 0.05, right? So if your alpha is 0.05 and your p-value is 0.03, then you do what? You reject the null. So if you reject the null, then that means your beta 1 is significantly different from 0. All right. And then the rest of the thing says use the f-test. Let me just quickly, I'll just show it, right? It says use the f-test to test the f-test to test the hypothesis in part D at alpha 5, and then present the results in the analysis of variance table here, no? So again, if we go back here and look at our run, let's see. Okay. I don't see my, so did I, to do this one, the easiest way or the alternative way is this. If you go to, let me make sure I don't confuse you too much, right? Because of this thing gets in the way. Your data set is here, no? And I want to compute the regression, including the ANOVA, no? So if you you should have installed your Excel stat in this case, no? And if you go to Excel stat, let's demonstrate that. If you go to Excel stat and what you're looking for is on the model and prediction here, no? So if you click here, you will see ANOVA and you will see regression, no? Linear regression. So make sure that, this is what we're looking for. So run your linear regression here, right? And now it's a matter of, again, make sure that you're specifying your variables correctly. So in this case, your Y values are over here, no? The Y values. And then your explanatory variable, so yeah, they use a different term, right? We use independent variable, or, right? In this case, they call it explanatory variable. So, and I'm going, so that's the X, no, the independent variable. So select those. And then if it's a qualitative one, then, you say it's qualitative. In this case, it's quantitative. So, okay, you keep it there. And then let's see, options, validations, predictions. For now, we'll leave that. And then your missing data, and then here's your output. So your output, you're going to want your descriptive statistics, which are shown here. Oh, here's my ANOVA here. And then my correlations. Okay, they give me that. Your analysis of variance, give me your standardized coefficients. Let's compute for those so that when you later on study that portion of the text, you can see where you can refer back to them. And then your charts, again, you can also do the standardized coefficient and so on. No? Okay, so if we click OK, here's your alternative way of coming up with your ANOVA and your what do you call it? Your regression, yeah? Your regression runs. So here again, little bit of different terms, right? A little bit of different terms are used. So we say your observations, and then here's your R square is what? R square is your coefficient of determination, no? Your coefficient of the determination. Here's your mean squared error, right? Then this is the square root of the mean square error. And then which is your standard deviation. And then you have your analysis of variance, right? And then you have your t-test also that, again, we've looked at, no? We've looked at before. Then what I also wanted to point out is, okay, so here's your estimated equation that you can use to predict or estimate the value of y given x. And then let's see, what else? Then we said to give us those computation of the residuals, no? So here's your residuals, and here's the standardized residuals, and then here's the lower and the upper bound for those residuals, you see. So the reason why I kind of bypassed going through the equations is you can put in the time and go through the equations, but once you understand what those equations are pointing to, then the computations can come in fast, and so it's quick. It's better at this stage to know where those results of the run are located. So and then here's the chart. Here's a similar chart that you see in the text, no? So here's your regression, and there's your coefficient, and here's your also your confidence intervals for the estimated, and then the confidence interval for your predicted value of y, no? Okay, but if we went back to here, I wanted to show that you can have the same statistics here. Let me close this one. And these are the same statistics that we got here, no? So you can, let's see, this is problem what? This is homework. What was that? 14 what? 14, 14.5, yeah? 45.1, no? Yeah, there's no 4 here. And then, so this run is for which one? Oh, I can't remember. Okay, so this one is also for work 14.1. Let's just put LR for linear regression. Okay, so the rest of it is, if I can move this away, we can see that what? If you go back, you can populate these values now, no? Either way, you can use the, what is that now? You can use the run that you got from Excel stat. So here's your ANOVA, no? Here's your ANOVA. And then you can also use, so two ways to do it, right? Where's the, yeah, there. Here's the run that you would have, this is the one that you got from your data tool pack, right? And then here's the one, I'm sorry, confusing now. Here's the one that you got from the data tool pack, no? And so here are those values, the 41, sum of squares due to regression, and then degrees of freedom, here's the degrees of freedom, and then substitute these values in, no? So, and then, so either way, you can use the Excel stat to come up with your regression estimate of your regression equation, and then the goodness of fit, and then your analysis of variance, or you can use the one that Excel provides, no? The one that Excel provides. Let's see. Is there anything else that beyond this one? That's the. Okay. So we got that one, no? We got that one. For the F test, again, you can see your F statistic. Where's your F statistic again on the run? You see your F statistic is here, no? And then your significance is over here. So let me see. Yeah. Okay. Save it. Okay. So let's see. So that was for section 5. Section 5, problem 1. And for the rest of them, I think it's probably similar, no? What about, let's see, just curious, let's look at problem 6, if it's probably similar. To make sure that we have enough samples. What is problem 6? Yeah, probably this. Yeah, it's the same one, no? So again, for section 5 and section 6, you can, even though it's asking you to use the formula, I wouldn't use the formula, okay? Instead, if you want to use the formula as a practice to gain an understanding, that's fine. But it's at this stage, it's quicker to make, it's easier to make the transition to, given the data set, structure it correctly in Excel, and then use either the regression function under the data toolpack, or use the Excel stat version of regression, and then it's a matter of interpreting the results. No? Okay, so I think I've held you back past the time, but do the homework, and then if you need anything or want some, send me an email for chapter 40 or 40. And then next week is our last regular semester, and after that it's our final. So let's see, let me go back to here. I'll just give me a minute. I think for our exam it's going to be it's December 14th, no? And it'll cover chapter 13, 14, and then 15. Okay. Okay, I'll see you guys next time. I'll post this video and also I'll post the worksheet that we did. Okay.